Okay, let's start. And any questions from last week? Any questions from online? Seems as though I'm already audible. Exam 2 Fridays from today, so it's November 14th, right? You'll all be voting tomorrow unless you already handed in your absentee ballots. I hope to have a review session either Monday, Tuesday, or Wednesday evening next week. I know I can't satisfy everybody with the time. Pick a time, we'll have the review session. The exam will cover up to and including definitely this Friday, but maybe also Monday. Friday, depending on how far we get. I'd like to get through momentum. And the first exam will then be from, I believe where we left off was acceleration in fluid masses to momentum. And again, if you can't make the review session, email me, set up a Zoom call, come by my office. I'm pretty available. Okay. So part 2, this is part 3. Yeah. So momentum problems, again, we have this very simple question. If the fluid control volume or the control fluid geometry changes dramatically in a short distance, which also includes a significant change in velocity. Again, a subset of all of this is fluid statics. So if there's no change in velocity, it's really not a momentum problem, it's a fluid statics problem. So if you have relatively significant velocities different than 0, then what's happening is you typically have a very unknown nonlinear pressure distribution over this portion of the control volume where the velocity is changing. And typically that's what we're after. How do we integrate that force to get a resultant force to represent that pressure distribution? And basically that's the force that this external system is placing on the fluid to get the velocity to do what it does. So we developed the momentum equation, and it basically says that for a control volume, the sum of the body forces, the external forces on the outside of the control volume, is equal to the time rate of change of linear momentum of fluxes that cross the control volume boundary. And again, this is a vector equation, so we have to pay attention to the fact that we have x, y, and z coordinates that we can apply this equation in. And typically we align z to be vertical and gravity is in this direction. And so the net result is weight is a force in the negative z direction. So whenever you have analyses that are looking at something in the vertical, you have to start including weight. And if you're after, again, a lot of times when we're calculating this force, we're trying to restrain against the force. In that case, your restraints not only includes the weight of the fluid, but the weight of the control volume. Let's say it's a big pipe fitting the size of this room. So that resultant force would also have to include consideration of the weight of the externality itself. So the forces are what we refer to as body forces. And again, there is a force of the control volume on the fluid. That is what's found with the momentum analysis. There's an equal and opposite force of the fluid on the control volume, and that's what we're designing against. And I gave you some examples. This is a slide you saw previously. So then I went through these methods, and I'm going to go through these quickly because you're going to see them on future slides. So as before with energy and all the others, I give you a rubric. Just follow the recipe and no one gets hurt. So again, there were 2 pieces to this, and if you follow the recipe, you can get through these types of problems. And then lastly, thinking of how we draw the control volume, obviously that's really important. And what we do is extend the control volume to either no flow boundaries or locations where we have one-dimensional flow. And where we have flow, we draw the control volume perpendicular to the velocity vector. So today I'm going to do 1, maybe 2 examples. So here's an example we're going to do a lot of today. And what you have is a Y fitting. So flow is coming up the bottom of this thing at location 1, and then it splits into 2 different directions, Q1. And obviously I didn't draw it in here, but from continuity, you know, if you have 20 CFS of water going in, water is flowing, and 8 CFS going out one end, then you know that what's going out the other end is the difference. Because that Y fitting can't store water. Continuity must be met. Some of the inflows is equal to some of the outflows, and there is no dV/dt, change in volume with time, because this system's already full. If this was a sewer that was not already full, then yes, you can actually store water in there temporarily. It's steady state, no. So you're given this Y fitting, you're giving the flows, and you're given the diameters, and you're also told at this location, we're calling it 1, you're given a pressure. So again, simple question. Obviously with Q1, we've got V1, we've got V2, and we've got V3. And the question is, do you see a dramatic change in the geometry of the flow field in a short distance? Yes, it goes from a single jet to 2 separate jets. And then also, is there a change in the velocity vector? Well, yes. First, the direction changes. You do not need a change in magnitude for there to be a change in the velocity vector. It could just be direction. So V2 and V3 are obviously not collinear with V1. And then added to that, they're probably not the same magnitude. We'll find that out from continuity. So here's the problem. We want to find the resultant force necessary to hold the pipe fitting in place. So that's basically the force of CV, the pipe in this case, the Y fitting on the fluid. And remember, that's what comes from the momentum analysis. Body forces, externalities. So you're going to see this figure on the next few slides, and you will note that 3 is 45 degrees off the horizontal and 2 is 60 degrees off of the horizontal. And you are looking in the horizontal plane. So you're looking down on this pipe. So all the flows are either in the X or the Y. They're all in the horizontal plane. So this is our problem, and this is what we're trying to solve. So again, you're going to see it on the next few slides, the same figure. And then on the left-hand side of this slide are all the steps. So first problem, is this a momentum? Is momentum involved? Is there a dramatic change in fluid geometry and velocity vector in short distance? Yes. So now you follow the rest of the steps. The next thing, we need to delineate the control volume. And so again, the control volume is going to go to where we have one-dimensional velocity vectors. And when you see it drawn in here, we have one-dimensional velocity vectors here, here, 2, and here. And then everywhere else outside of those 3 locations, it's just the skin of the pipe. That's a no-flow boundary. So that's our control volume about which we're trying to do the momentum analysis. It's hard to do a momentum analysis, especially for someone to review your work, if you don't show them what your control volume is. All right, the next step is to identify the coordinate axes, X, Y, and Z. And in this particular problem, we're just going to say that X is perpendicular to where 1 is coming in, and Y is collinear with 1. And again, the whole problem is in a horizontal plane. You could have made X and Y with respect to any dimension you want. However, it's kind of convenient to relate it to the geometries that you were given in this problem. So pipe 3 is 45 degrees off of this horizontal X direction, and pipe 2 is 60 degrees off that same horizontal direction, or we could have referenced them with respect to the Y direction. So pipe 1 is collinear with the Y, pipe 2 is 30 degrees off the Y, and pipe 3 is 45 degrees off the Y. So again, X and Y can be anything you want, but don't make it difficult on yourselves. Any questions? Just out of curiosity, how many students are logged on?
69.
69, I'm impressed. Obviously, it should be more like 90, but it was dipping even lower than that before. So the next thing we're going to do is identify an elevation datum. So in this case, what we know is we're looking down on a horizontal plane. So all we're going to say is that Z is equal to 0 in the plane of the fitting, say the center line of the pipes. So if we looked at this thing, here's the 18-inch pipe coming in, and these are the two pipes going out. There's two of them, one over the other. And so this is where Z is equal to 0, right along the center line of the pipes. Next thing, identify all fluxes crossing the control volume boundary and their directions. So I think you can see Q1, Q2, and Q3 have been called out. And so we know what those fluxes are, and we found Q3 by continuity, and we know their directions. Their directions are important because that direction is associated with the velocity vector at each location, which is going to factor into one of the two sign conventions used for the momentum flux terms, rho QV. The next one, locations where pressures are either known, assumed, or calculable. And I think you can see down here, P1 is 10 PSI. There's no reason to believe that there is a free jet at P2. You can see the pipes cut away, and there's also a P3 here. And this is P1. Okay, so we've identified locations where we know the pressure. All over the rest of the surface, all over the skin of the pipe, there are pressures. And we're going to wrap those all into a resultant force. We don't know what those pressures are. They're very difficult to calculate. So the next thing we're going to do is to delineate all forces and their directions acting on the control volume where the pressures are known. So at the bottom, F1 is going to be P1A1, right? And we already know P1 is 10 PSI. Up at location 2, we have F2, and F2 is going to be P2A2. And over by 3, F3 is P3. Okay, so we have those forces now, and they're all where we know the pressures. The next bullet, where the pressure distribution is unknown. And again, that's all over the inside of the pipe, away from P1, P2, P3. That's P1, P2, P3 is where we know the pressures. So in this case, what we're going to say is we're going to have this resultant force R that represents all of this pressure distribution we don't know. I'm assuming it's upwards and to the left. That is an assumption. You can assume any direction you want. For example, you could have assumed that. It's going to come out in the wash. But there is a large portion of this control volume where we do not know the pressure distribution. And that's all being lumped into R. So once we know this, now what we can do is perform the momentum analyses. We may need continuity to help us out with pressures and velocities. Because right now, if you look at the momentum equation, we know the pressure at 1, and we know the discharges at 1, 2, 3. So from continuity, we can get the velocities at 1, 2, 3, but we don't have P2 and P3 yet. So following these in order, for the velocities, we know we have Q1, Q2, and Q3. And so V1 is Q1 over A1. So Q1 is 20 cubic feet per second. And A1 is pi over 4 times 18 inches, which is 1.1 foot squared. And that's equal to the 11.3 foot per second. Okay. So I don't think I need to bore you with continuity now, but we're doing the same thing at location 2 and 3. We know the discharge, we know the pipe diameters. At location 2, the pipe diameter is 6 inches, the discharge is 8 cubic feet per second, and we get a very high velocity of 40.7 feet per second. At location 3, the pipe diameter is 1 foot, 12 inches, and we know we have 12 cubic feet per second. So again, that gives us 15.3 feet per second. So not only is our V2 and V3 different in orientation from V1, but they're different in magnitude. Okay, so we'll have these 3 velocities to continue.
Robert didn't ask about the pressure at P2 and P3.
We'll get to that. Patience. Okay, so there are our velocities. Now, interestingly, the question just came up, what about the pressures? So how are we going to solve for the pressures? This is a horizontal pipe. And let's go, for example, from 1, which is an 18-inch diameter pipe, to 2, which is a 6-inch diameter pipe. And we know that we have 10 psi at location 1. We also said that along this center line, Z is equal to 0. You know the velocities at 1 and 2, you know the elevations at 1 and 2, you know the pressure at 1. Is there anything in your history or your recent memory that would help you find P1? Bernoulli equation, energy equation, right? And so if you look at this, P1, we know we have 10 psi. For P2, we'll just write a Bernoulli or an energy equation from 1 to 2. Remember, what's happening is at this point in our career, this is our energy grade line. It's a constant value all over the whole system. And what's happening is we've got, for example, the hydraulic grade line is different from the energy grade line by V squared over 2G. And then the distance between the hydraulic grade line and the pipe is P over gamma. Okay. So basically all we're saying is that this elevation is equal to that elevation. B1 is equal to B2. And that's going to be on the next slide. So similarly, B1 is equal to B2 is equal to B3. You can write a Bernoulli's from 1 to 3. Now that you know everything at 2, you can write it from 2 to 3. You're going to get to the same answer. So looking at these energy statements, from 1 to 2, we would say the velocity head at 1 plus the pressure head at 1 plus Z1, B1 squared over 2G plus P1 over gamma plus Z1 is equal to the Bernoulli sum. And that's equal to the same thing at location 2. And there's only one unknown in this equation now, and that's the pressure at 2. So we know that Z1 is equal to Z2, which is equal to 0. They're on our datum, our elevation datum. V1 from the last problem, from 2 slides ago, we calculated from continuity to be 11.3 feet per second. V2 we calculated to be 40.7 feet per second. And so now what we can put in here, knowing that P1 is 10 psi, we would say that 11.3 foot per second squared over 2 times 32.2 foot per second squared plus 10 psi times 144 inches squared per foot squared divided by 62.4 pound per cubic foot. Remember, this was water, is equal to 40.7 foot per second squared. 2 times 32.2 foot per second squared plus P2 over 62.4 PCF. So again, there's only one unknown in that equation. And so we would just go through this exercise and calculate the pressure at 2. And the pressure at 2, in case I wrote over it, is minus 44.4 pound per square foot, which is minus 0.31 PSI. So again, from the sketch that I did before, our energy grade line is here. And what happened was we went from an energy grade line here, sorry, hydraulic grade line, to now the hydraulic grade line being below the pipe. That's how we got the negative pressure. Can this happen? Of course it can happen. All we did was we decided to steal a lot of P1 and put it into V2. Again, that's all you're doing with energy conversion. You can convert from elevation to pressure to velocity any way you want. And somebody's going to pay the price. In this case, the pressure paid the price. So that's how we calculated P2. And we're going to do the same thing for P3. So we would now write our Bernoulli equation. In this case, I chose to go from 1 to 3. Again, you would get the same answer if you went from 2 to 3. As before, we know that both of the elevations are on our datum. As before, we know the velocities from continuity. And as before, we know the pressure at 1. And so what we would do is get a very similar equation to what we just had, only instead of the subscripts of 2, we now have the subscripts of 3. And we would solve that P3 is 1338 pounds per square foot. So I just want to reiterate 10, 1.3 PSI, and this actually looks like this. So it's 0.31 PSI when you draw it like that, and when you draw it like this, it's minus 0.31 PSI. And I had mentioned before what happens when you get negative pressures. Just be consistent. I usually keep this form, and it'll work its way into the force vector. Okay, so don't turn the pressure around when you get a negative pressure. Just keep it this way and keep that negative sign there. But I want you to see something incredibly important, because you have people who colloquially work with pressure distribution systems. For example, the Public Works Department. And their thought is water flows from high pressure to low pressure. And in fact, that's what you see here, that the 2 other pressures are lower than the 10 PSI. But you could easily, if you had gone to a larger cross section, had flow going to a higher pressure, from low pressure to high pressure. Why? Because flow goes from the high energy to the low energy. And by just looking at pressure, you're not considering elevation or velocity. So just keep that in mind. Fluids move from high energy to low energy, not high pressure to low pressure. You can easily have flow going from low pressure to high pressure. Okay, so when we solve all of that, here's our momentum example. And again, what we're trying to do is solve this equation. And in this case, we're doing it in the x direction. So if you recall, that was our plus x, and this is our plus y. And so what we're trying to do on the left-hand side is to look at our forces And you will notice that each of the forces has an x component. And there is no x component in the force at F1. F1 is all directed in the y direction. And again, that was intentional. So if you know these angles, 60 degrees, then F2x would be F2 cosine 60, F3x would be F3 cosine 45. So they're pretty straightforward. So in the x direction, what we would have first is, this is P2A2 is F2x. And for F2x, that's F2, P2A2, that's F2. And then the cosine of 60 is what makes it F2x. Because I'm just looking in the x direction. That's one of the terms, not all of them. And then the next term, you will see that F2x has a positive sign in front of it, but you typically don't write the positive signs when it's the first one. So P2A2 cosine 60, which is F2x, is in the positive x direction. Conversely, F3x is in the negative x direction. And so after we have P2A2 cosine 60, the next term would be F3x. And it's a negative sign because it's in the negative x direction. And again, F3x is F3 times its component in the x direction. So that's P3A3 cosine 45 degrees. And then the only other force that has an x component, we assume this was R. And so this is Rx for that assumption. And that Rx is in the negative x direction. Any questions on that? On all those forces and all their signs? Remember, the forces subscribe to one sign convention, the x and y coordinate axis system. The momentum flux terms, rho QV, subscribe to two sign conventions, not only the positive x and y, which gives you a sign on the velocity vector, but the rho QV term is positive if it's out of the control volume, negative if it's into the control volume. So for the rho QV terms, we've got the first term, rho Q2 V2 cosine 45. So here at location 2 is rho Q2 V2. Is it entering or leaving the control volume? It's leaving. That's a positive sign. Look at the velocity vector. The velocity vector for that flow is in the negative x direction. Positive times a negative is a negative. That's why you see the negative sign in front of rho Q2 V2 cosine 45 degrees. So the total flux is rho Q2 V2. The flux component in the x direction is, that should be 60 degrees, shouldn't it? That's what happens when you copy and paste. Rho Q2 V2 cosine 60 degrees is the component of the momentum flux in just the x direction. And then we apply the two sign conventions. It's leaving, positive. The velocity vector is the negative x, negative. That's what gives us a negative. Any questions on that sign convention?
Well, that's, I guess that should be rho Q3 V3.
Yeah, it should be. I copied and pasted. Okay. And similarly, at location 3, we have rho Q3 V3, and it's got a component in the x direction, rho Q3 V3 in the x direction. So that x component, again, just like the forces, is cosine 45. Rho Q3 V3 cosine 45 degrees is the component in the x direction. And two sign conventions. It's leaving the control volume positive. The velocity vector is in the positive x direction, positive. Positive times a positive is a positive. That's why we have a positive sign in front of it. There is no component of the momentum flux in the x direction at location 1. Location 1 is all collinear with the y. And so when you look at this equation, sum of the forces, we know everything on the sum of the forces terms except Rx. For the momentum flux, we know both the rho Q V terms at 2 and 3. The only unknown in that equation is Rx. So when we go through and calculate it, we find that Rx is minus 683 pounds. What does that mean? It means you guessed the wrong direction. So if this Ry was correct, basically you would have that Ry, and now you would have an Rx, not to the left, but to the right of 683 pounds. This is minus 683 pounds. So when we assumed it going to the left, it's a value of minus 683 pounds. If we more appropriately identify it as saying, well, that means it's 683 pounds to the right, then our resultant vector would look like this. So again, when we start off this problem, we just assume a direction for the resultant force. And when we go through the analyses, the direction will come out of our analysis. Any questions on this? Yeah.
You use 1.94 for the density?
Yes, so density of water is 1.935 or whatever, 1.94 slug per foot cubed. And then you multiply that by the discharge in cubic feet per second, and you multiply it by the velocity in feet per second, and you get slug foot to the fourth per second. And again, that's equal to a pound. We went over that. When you use slugs, that's MLT, and we typically do all of these analyses in FLT. So the dimensions are all consistent. Okay. Okay.
So I have another question. Is P2V is negative for 2?
Yeah. So P2 is, that's where you would put the minus 0.31 psi, and that's what would flip its sign around. Yep. Yep. Exactly right. We see more questions coming in. That's the beauty of having the TAs here. They can handle a lot of the questions online. They only refer a question to me when they want to make sure I'm awake. So now we're going to look at the y direction. And again, plus y and plus x look like this. And so location 1 is collinear with the y direction. And when we look at these other two locations of either rho QV or the forces, each of those has a component in the y direction. So first we'll look at the left-hand side, the sum of the forces. So the first thing we have is P1A1. And again, that would be F1 due to the pressure distribution at the bottom. And then at location 2, F2y is F2, which is the pressure 2 times the cross-sectional area 2. The component in the y direction is now the sine of 60 degrees, and it's operating in the negative y direction, just like force 1 was operating in the positive y direction. And so we follow that sign convention for each of the forces. After those two, we see that again, at this location, we have a rho Q3 V3 term, and we have an F3 term, and F3 also has a component in the negative y direction. And so we need F3y, because we're just interested in the y direction. So again, we have a negative sign because F3y is in the negative y direction. F3 is P3A3, and the component in the y direction is sine of 45. And then again, this should have been plus. We assumed, oh no, yeah, that's right. We assume this for R, and that has components in the negative x direction, which we've just discovered was the wrong guess. And our assumption was with that original line of action for the resultant force R, it's got a component in the positive y direction. For the momentum flux terms, you're going to have a momentum flux term in each direction. And so that's going to be the rho QV at 1. Rho QV at 1, it's entering, that's a negative sign convention. And the velocity vector is in the positive y, positive sign convention. Negative times a positive is a negative. Rho Q1 V1, no sine or cosine term because it's all directed in the y direction. For location 2, this is rho Q V 2y. And so we see it's leaving, that's a positive sign, and the y component of the velocity vector at location 2 is also in the positive y, hence the positive sign. That should be a 3, that should be 60, that should be a 3. And then at location 3, again, we have the momentum flux rho QV at 3 leaving the control volume, positive sign. The velocity vector component in the y direction at 3 is in the positive y direction. And so positive times positive is a positive. Rho Q3 V3 sine 45 is the momentum flux component in the y direction at location 3. And so just as before, the only unknown in this equation, sum of the forces is equal to the sum of the rho QV in the y direction. The only unknown is Ry. And when we go through and solve it, we get Ry is equal to a minus 1450 pounds, which means we not only guessed the wrong direction for the x component, but we guessed the wrong direction for the y component. It's not fatal. It was an assumption. So if we look at this, this is what we assumed. We assumed that we had Rx and Ry in these directions. And what we found was that the first one was minus 638 pounds. And the second one was minus 1450 pounds. So we use those negative signs to just have those component vectors go in the other direction. So our final analysis would be that this is the direction of the resultant vector. It's got a component to the right now of 638 pounds. And it's got a vertical component downward at 1450 pounds. Right? And now that you know the two components, we know that we can get the total magnitude of the resultant vector, this is the magnitude, is going to be equal to Rx squared, 638 pound squared, plus Ry squared, 1450 pound squared, all to the radical sign. And that gives us a total value of 1603 pounds. And what we would also recognize is we could either look at the angle off of the vertical, I called that theta, or we could look at the angle off of the horizontal. Half a dozen of one, 6 of the other. It's a right triangle. If you know one, you know the other. So in this case, if we define the angle between R and the vertical, the y-axis, then cosine of theta would be Rx divided by R. And therefore theta is 64.8 degrees. So now you know the line of action of this force. Questions? The question asked at the very beginning what is the force of the pipe on the fluid? That's what you just found. If the question asked, what's the force of the fluid on the pipe? It would be equal and opposite. I think I've said that over a dozen times in here now, but that's one of the first things you need to look at. You know, it only costs you a point or two here. When you leave here and you design something, that's not a happy face when you actually assume the wrong direction for a force. Okay, so if there's no questions on that, what I want to do is, in the last 10 minutes, broach this topic, and then we'll continue with it next time. So I want to first talk about fixed vanes, and then we're going to move to moving vanes, okay? Moving vanes are what are inside pumps and turbines. And what you're trying to do is convert kinetic energy to pressure, and that's done with momentum. So typically for the vane problems, the most important thing is that you have free jets. That makes life so easy for you, as you will see. Because if your control volume goes out to a free jet, the pressure in a free jet is atmospheric. And if you work the problem in the atmospheric pressure or gauge pressure datum, all those forces are zero because all the pressures are zero. Very convenient. And so typically for the fixed vane problems, the only force you're looking at is the force of the vane on the fluid. That's the only thing in the sum of the forces term. So for example, here's a vane. Think of it as a plate. So you're looking at the edge of the plate, and the plate might be just a rectangle. Okay, and you're looking at the edge. And assume, for example, that you're actually looking in a horizontal plane. So here's the plus X and here's the plus Y. So you're looking down on this thing. And so what could happen is, for example, you've got this flow coming onto this plate. Again, we call it a fixed vane, but it's just a plate. And so this is a free jet. And it's coming in at Q0 with a velocity V0, and it of course has a cross-sectional area A0. So Q0 is V0, A0. Okay. And then let's say that this plate perfectly splits the flow. So, simple question. Is there a dramatic change in the geometry of the flow field in a short distance? Yes. If you didn't have that plate there, this fluid would not be splitting like it does. It would just keep going in a straight line. And in fact, if nothing was holding that plate in place, would it stay there? No. So what's happening is there's some nonlinear pressure distribution on the backside of this plate, pushing against the oncoming jet. And that is integrated into, and I'm going to draw it like this, integrated into this resultant force. I'm assuming a direction for it. I'm assuming it has X and Y components. Maybe it doesn't have a Y component. I can go through the analysis and find out it'll be zero. Okay. So this is what's happening in this problem. And so typically what we're after is this resultant force. What's the force we need to for that plate to be applying to the fluid? All right, so we're going to see the same thing. I'm just going to redraw it for you. And we follow this all the time. We're following this procedure. So the first thing is to draw the control volume. And how we're going to do that is here we have one-dimensional flow. Out here we have one-dimensional flow. And so we're just going to have the control volume. I figured out how to use colors finally. This is our CV. It's all the fluid, and we went out here for a few reasons. One, at all those locations, again, it's one-dimensional flow. But two, those are free jets. If you had gone back somewhere onto the plate, it's not a free jet now. There's a pressure distribution at the bottom of that fluid, and it permeates to the top of the fluid, where yes, up here at the top of the fluid, you have atmospheric pressure, but not throughout the rest of that water flowing against the surface. So you extend the control volume to beyond the plate. And so again, we're going to be solving the momentum equation. And what I'm drawing is the pressures on the end. So this is P1, P2, P3. And F1 is going to be P1A1. But all of those pressures are atmospheric. So all those forces are zero. That's the key thing to understand in the vane problems. So we're going to be subscribing to this table, but I want to go through it. So for this one, again, here's our coordinate axis, plus X, plus Y, and we have a control volume. And we're going to have 1/2 Q0 here, 1/2 Q0 here, and Q0 here. And we have B0 and A0. So you're looking down on a horizontal plane, and we see this, and then we just identified that everything in here is our control volume. So we're going to be solving this equation in component directions. So for example, we can first look at the X to the right being positive. And we said this is going to be R, so we're going to have Rx in the negative X direction, as assumed. So on the left-hand side, the sum of the forces, well, we've got F2, F3, F1. But as I said before, since they're all free jets, they're all zero. All you have for the sum of the forces is minus Rx. That's it. Now, momentum fluxes. If you look at how we constructed this problem, location 2, which is above, and 3 are collinear with the Y. They have no components in the X direction. Could you have a problem where it's skewed? Absolutely. Then those locations at 2 and 3 would have components in the X and the Y. But in this case, there are no X components at locations 2 and 3. So this would be rho Q0, B0. Now that's just the rho Q B0 term. It's all directed in the X direction. Now we have to apply the two sign conventions to it. Entering, negative sign. Velocity vector, positive X direction. So Rx is basically just the momentum flux term. That's how much you would have to force hold against it. It's how they design water cannons. They want that rho QV larger than what the human body can resist. It's pretty simple. So in the Z direction or Y direction, upwards positive, in the Y direction. The sum of the forces, again, there is no component of force in location 1 at 0 coming in because it's all directed horizontally. So the only possibilities would be at 2 and 3, F2 and F3, but we've discussed this ad nauseum. They're free jets, so their forces are 0. So the only thing you're left with is Ry, an assumed Ry. And you have a flux going upward and a flux going downward. If we look at location 2 and location 3, so at location 2, we've got rho 1/2 Q 0 V2. It's leaving, and the velocity vector is in the positive X direction. Positive times a positive is a positive. And then the other term is rho 1/2 Q0 V3. It's leaving, but the velocity vector is in the negative x direction. So our y is rho 1/2 Q0, since that's the flux, V2, minus rho 1/2 Q0 V3. It would be really nice if we had an equation that could help us estimate or calculate V2 and V3. We can't use continuity because we don't know the cross-sectional area. So any other equation in your toolbox? Like energy? So I'm writing an energy equation from location 0 to location 2. This is in a horizontal plane. Z0 and Z2 are at the same elevation. They're right at the center line of this system as you look down it. V0 and P0 and P2 are both free jets. So what does that tell you about V0 and V2? They have to be the same, right? And if you did that in the 3 direction, you'd see that V0 is equal to V2 is equal to V3. Water has to leave the plate as fast as it comes on. So what does that mean? That right-hand side is 0. And so there is no Rx. R is all horizontal, as you'd expect. Right? It wouldn't be true if this was tilted in one direction or another. So that's the vein problem. I know I'm about a minute over. Are there any questions? All right, then. We'll continue with this next time with numerical examples. We're going to curve it and make it a little more challenging, but these are the fundamentals. See you Wednesday.